Okay, so this is part of the group of videos for acids and bases is explaining the table. So explaining each column of the table and what do you need to know in regards to the table. This table, as you see in your data booklet, is divided into 2 pages and it is turned landscape format. Okay, so I will explain it as you see it like this, but you probably have to turn the video or the format of the video. Let me try it. The first column of this table, it's the name of the acid. So pretty much, in other words, you don't need to remember any of the acid names that you have seen or done. It will help you if you somehow remember or have an idea of the name, but pretty much the common name or the IUPAC name of the acid is given here. So this will be the name of the acid. And then the other column is giving you the formula of the acid. So the proper formula of the acid is given here. We will talk about what is a conjugate base and what is this formula here. And then the very last column of it is dealing with the Ka value of the acid. However, what do we have to keep in mind is that this group of acids here, it's known to be strong acids, okay? And then hydronium is dividing the strong acids with those that are known as the weak acids. We will talk about them. What is the difference between each of them in the following video. Okay, now this table is kind of similar to the table that we saw at the electrostatic with the electric potential voltage. But what we have here is those weak acids, they start from the top being the strongest and going down being the weakest acid. So this is strong acid. What we are saying here is that oxalic acid, which is right at the top, is stronger than butanic acid or any acid that is below it. And a difference with the bases, they start at the bottom being the strongest one and then coming up as the weak bases. Okay, so what we are saying here is that those conjugate bases, let's say this one here, is stronger than this one here. Okay. Another important information that you need to see and discover or talk about in this table is that when we see those numbers here, they don't have any because it is very large and it is considered to be, those are strong acids. They are considered to be the fully 100% ionized. On the other hand, those numbers here are telling us what is the Ka value of each of those weak acids. Okay, so now remember what we said at the end of the previous video when we talked about auto-ionization of water, that Kw is equal to Kb times, or the value of the concentration of the the hydronium times the concentration of hydroxide. So this is a different way to figure out as well. It is accepted that those acids are weakly less than 5% ionized, and this is why they are called weak acids, and their constant of equilibrium is given here. It's considered to be constant value, and this is, again, it's at a certain temperature, 25 degrees and so on. Okay, so this is in terms of the table. Okay, so now let's see how can we use this table and what can we do with this table further into defining the strong acid, defining the strong base, and talking about conjugate base and so on. Okay, so when we are identifying an acid or base based on Arrhenius and modify Arrhenius, what we were saying is that it is able to release into a solution a proton, and then this proton is attached with a water molecule to form that hydronium. However, there were things that were noticed that were not properly justified. The logic didn't go very well with them. So then Bronsted and Lauder, they formed, or they talked about a way to define which one is acid and which one is base. So Bronsted and Lowry definition of an acid is that they are proton donor. So if a compound is able to donate a proton, it's considered to be an acid. And if it is a base, is a proton acceptor. Okay, so if accepted, then it is it is considered to be a base. Now, the term conjugate base or conjugate acid comes from mathematics. So in mathematics, when you are simplifying the denominator, what you are saying is you're saying that it's the same thing. So if you have A plus B here, the conjugate of A plus B is A minus B. Okay, so those two are conjugate of each other. It's the same characteristics with a small change. In math is with negative. And in chemistry, the conjugate base or the conjugate acid is the same thing. So we have, if we have, let's suppose, hydrochloric acid in water. Okay. Hydrochloric acid in your data table, it's one of the strongest acids. So it's this one here. It's this one here. HCl. This one here. Okay, so it is, which means that will be 100% ionized. This is why when we are writing it in water, we just go in one direction, because will be 100% ionized. So what is happening here? This compound, which is hydrochloric acid, is donating the hydrogen to water. Okay, and it is forming a hydronium in aqua solution, the liquid aqua solution. Then Cl minus is left over. Now, in this case, since hydrochloric acid is donating the hydrogen, is considered to be acid, which leaves the acceptor of the hydrogen as a base. Okay, and now the one that is turned into, from base, accepting it, it's turned into, it is considered to be a conjugated acid. And the one that is left as a result of the donation of the hydrogen, it's becoming a conjugate base. So an acid is becoming a conjugate base, while a base is becoming a conjugate acid. Okay, let's see another example. Let's suppose that we have ammonia, NH3, that is acting as a base in water. Okay, so what is happening here, since it is becoming a base, it is taking one hydrogen from water, which can be base and acid, and it is becoming NH4 plus. Okay, so this is base and this is acid, because it is donating the electron, the proton, sorry. And then what is left is hydroxide. So the base by accepting one electron, one hydrogen, sorry, it's becoming conjugate acid. And the acid, by donating that hydrogen, is becoming conjugate base. So base becomes a conjugate acid, and acid becomes a conjugate base. In other words, how can we identify a conjugate base and a conjugate acid? Okay, so let's suppose that is water. The conjugate acid of water is someone that is grabbing the electron. So it's the kind of the same thing plus one H plus. So when we see it, then H2O plus one hydrogen will be H3O plus, because hydrogen is H plus. So for the conjugate acid, what you do is you add a hydrogen plus. And when you are looking for the conjugate base of a compound, then what it is happening, it is subtracting or taking away hydrogen plus. So when you take away a hydrogen plus from water, what it is left is hydroxide. Okay, and even on the other example that we did, NH3, when we have a conjugate acid of it, then what we do is we add an H plus, and adding an H plus to NH3 will become NH4 plus. Okay, and when we are looking for the conjugate base of NH3, we subtract an H plus. And by subtracting an H plus, this will become NH2 minus. And this is the same thing. If we have, let's suppose that we have H2PO4 minus. It is in your data booklet. When we are looking for conjugate acid, what do we do is we add a hydrogen plus. by adding a hydrogen plus. So this will become H3PO4 because minus 1 plus 1 PO4. And when we are looking for conjugate base, what do? We take away a hydrogen plus. And by taking away a hydrogen plus, we are left with one hydrogen PO4, 2 minus. If we go further and say now, okay, what is the conjugate acid of this? Then we add one hydrogen. By adding one hydrogen, we'll go to H2PO4 minus. And when we are looking for conjugate base of this, then we take away one H plus, which means that this will be PO4 3 minus. Okay, so this is the conjugate base and the conjugate acid concept. And in your data booklet, what do you have is the conjugate base of the acids. So what it is actually one of the hydrogen is taken away. So take any of them. You will see, let's suppose this one here, H2C6, H6O6. And when you compare it with the conjugate base, it is one less hydrogen on it. So now if we talk about the differences between strong acids and weak acids, so strong acids and weak acids, what we have to keep in mind is that strong acid will be 100% ionized. So all hydrogen plus will be converted into hydronium ion. They are strong electrolytes in water because they form the hydronium ion. The way that we identify the strong acids are at the top of your data booklet. Whatever is above the hydronium ion is considered to be the strong acid. On the other hand, what is happening with the weak acids is the ionization is barely happening there. So they ionize less than 5%. They, of course, since their ionization is very low, then what is happening is they are weak electrolytes. So they don't conduct electricity very well. And weak acids in our data booklet are the ones that are below hydronium. I will say here at the bottom of your data booklet. And what I mean is this, that those are strong acids and those are weak acids. Okay, so everything that is above is strong acid and everything that is below is weak acids. Okay. One thing that you probably will help you not only on this course, but even on the other courses, is that acids with more, that are look the same, but they have more oxygen atoms are stronger. So as you notice here, even on the table, we have, let's say, H2SO4 and H2SO3. H2SO4 is stronger than H2SO3, okay? Or HNO3 is stronger than HNO2, okay? Or HClO4, which is one of the strongest acids, is at the top, is stronger than HClO3, stronger than HClO2, stronger than HClO, but if the stronger of all is HCl, because it doesn't have any oxygen. So it should have an atom of oxygen in order to kind of use this as a strategy for defining which one is stronger and which one is not. Now, how do we write dissociation or reaction with the strong acids and weak acids? The only difference is that they always are forming a hydronium, but the only difference is that a strong acid, the reaction will be something like this when it is dissolved in water. Will be going in one direction where it is forming a hydronium and a chloride, aqueous, and a weak acid will be the one in which they are in equilibrium, which means that they will have something like water will be with two arrows and will be F minus in aqueous solution and hydronium. Okay, so what is happening at the weak acids is an equilibrium, and this gives us even the right to say that we have a value of Ka for those. Now, strong bases and strong acids, we'll do this and then we'll close with this video. So now strong bases versus weak bases. A strong base is completely ionized. So a strong base is someone like potassium hydroxide or sodium hydroxide or barium hydroxide. They are ionized completely. Ionized completely. Okay, they are soluble and they are strong electrolyte, therefore, because they are ionized completely. Strong electrolyte. And 100% ionization. And what is happening with weak bases? The weak bases are bases like OH3. It's insoluble. They are not soluble. So it is less than 5% ionization. And they are insoluble, weak electrolytes. They don't have enough ions. Weak electrolyte, and as I said, that they are less than 5% ionized. One thing that we have to keep in mind is that when we are talking about strong base and strong acids, or weak base and strong bases, we have to put a note here that when we have O negative 2, it's considered to be a strong base. A strong base. Because what is happening with O2 is grabbing the hydrogen, and then it is forming 2 hydroxide. So the reaction will be something like this. Okay. And the same thing as when we discussed what we said with acids. The more we said that the more oxygen, the stronger acids they are. Even here, it's pretty much the same thing. The more hydrogen, the less hydrogen, the more stronger they are. So O2 is a stronger base than OH minus, than H2O, than H3O plus, okay, which is actually acidic. Okay, so this is for the table and the difference between strong acid, strong base, and strong acid, weak acid, strong base, weak base, and conjugate. Keep in mind that when you are writing a reaction for weak acids, you have to write it as the equilibrium that goes in 2 directions.